Today, this is our online class for all students, all Engineering Mechanics 2 students, and we will practice the Chapter 4 problems. We already started with one of the problems, and at the end of the class or after class, there is time for additional questions. If you have any right now, we will have this time every week from now on. Okay, so let's have a look in the script and where we stopped last time. Okay, so we started solving problem 414, this car carriage on a ramp, and we already drew the free body diagrams for both subsystems, for the carriage of mass m1 and the ramp of mass m2. And now the next step is solving the systems. That means we need to build the equilibrium conditions. For example, for the carriage, we could build them parallel and perpendicular to the ramp, the incline, and then for the ramp in horizontal and vertical direction. And then we need to solve for the acceleration A2, the acceleration of the ramp, and the acceleration AR, the relative acceleration of the carriage relative to the ramp. And as last part of the problem, we have to solve for the time that the carriage needs to travel a distance of 3 meters on the ramp. Okay, so please try to solve the problems on your own, state the equilibrium conditions, rearrange the conditions to solve for the unknowns. I will open the breakout sessions. If you have any problems, ask me, call me into your session, or ask me in the main room. I will go through all the sessions and ask for questions. Please try to solve it on your own to practice these type of problems. Okay, let's start. I open Okay, sorry, I chose the wrong options for the breakout sessions. Of course, you are free to choose your own room, your own session with your friends and your classmates you like to work with. So let's start again with these sessions, and now you can choose your session on your own. Okay. So we have 10 rooms, 10 breakout rooms. Of course, can either talk to your friends and choose a room where you want to work, or you can stay in the main room, in the main session as well. If you're already finished solving the problems, or when you are finished with the problem, just give me a small hint, like a information in the chat or something like that, such that I know that you're finished. Or if you have problems, then also ask in the chat or just talk to me.
Ma'am, I have a doubt.
Yes.
The two normal forces, can they be combined into a single force?
The normal forces 1 and 2 as depicted in our problem, or which normal forces?
Yes, those two forces.
No, because they are they depend on different variables and they point in different directions. And 2 points in vertical direction upwards, and N1 points downwards under the angle beta. So N1 and N2 are both unknowns. But of course, you can rearrange your equation and substitute for N1, for example.
Yes. Okay.
Okay.
Thank you.
Mhm.
Excuse me, Professor, for the gravitational acceleration, should we use 10 or 9.8?
You can use 10. If there's nothing stated in the problem description, you can choose either 9.81 or 10, but I think easiest ways, just always choosing 10 meter per square second.
Okay, Professor.
Mhm.
Professor. Excuse me, Professor. I think she's here.
Okay, let's have a look at the solution. So, as we already discussed, you have to build the equilibrium conditions. We can only build the sum of all forces. We cannot state the momentum equations since we have no dimensions of the system given. But we do not need them. We can solve the problem without them. So we need two equations for the first subsystem. Then for the second subsystem, the horizontal, the ramp, the horizontal direction is sufficient. We do not need the vertical direction of the equilibrium condition since we are not interested in the normal force N2. And then we can rearrange, substitute the equations into each other, and we obtain the two accelerations A2 and AR. Okay, are there any questions up to this point? Okay, if not, then yes.
Maybe just one. Sorry, is there any intuition about what we should rearrange in what? Because I solved everything, but I had a lot of calculation because I need to spend time to understand what unknowns I need to substitute on what. Is there any intuition behind it?
Yes.
Actually, I have the same issue. I like did 2 pages of calculation to get to the same results that you did. So.
Okay, so let's have a look at the problem. We have the free body diagrams. There is no options there. So this is the only possible solution for the pictures, for the free body diagrams. Then once we derive the pictures, we can decide. I will write here on the side. Okay, we can decide, or we can have a look at the unknowns. So which ones do we have? We have the normal forces N1, N2, A2, and AR. These are our unknowns. Everything else is given in the problem description. So what are we interested in? According to the problem description, we want to solve for A2 and AR. Then this means we are not interested at all in the normal force N2. And if we have a look at the ramp, at the free body diagram of the ramp, our normal force N2 acts in vertical direction. And the only component of interest in the free body diagram of the ramp is the force A2. Then A2, M2A2, the inertial force, acts perpendicular to the normal force N2. So there is no need at all to solve the equilibrium condition in this direction. It gives no information for us, no information in which we are interested. Also, for the first subsystem, there are all of our unknowns in this free body diagram. Also the normal force N1, but we are not interested in the normal force N1. Then we do have to substitute N1 from here into this equation. So if we substitute the unknowns that we are not interested in, we will automatically obtain the unknown values that we want to compute, A2 and AR.
Yes, perfect. Thank you.
Yep. Okay.
Thank you.
Okay, then the second part of the problem, wait, what we can do is we can solve for the absolute acceleration A1. It's not asked for, but just to be complete, I would like to do this as well. So as stated above, our absolute acceleration of the carriage consists of translation as the ramp plus relative acceleration. Now this is a vector equation. Right now, we do not know the direction of our absolute acceleration. I will use this x as our center of gravity of the mass M2. What we do know is that A2 points in this direction and AR points in this direction. Now we can assume the components of the acceleration a1, of the absolute acceleration, like this. a1y and a1x. Okay. Now with this assumption, we can state the vectors. So we do not have to decompose a2 since it points in horizontal direction. We only have to decompose the relative acceleration. So here it would be minus AR cosine beta and AR sine beta. And then from this, we obtain the components of the absolute acceleration with minus 4.145 meter per second. Since it's negative, this means that I assumed the wrong direction. The horizontal component of the absolute acceleration points to the left, not to the right. But of course, that doesn't matter. 2.632 for the vertical component. Okay. Again, it wasn't asked for in this problem, but it could have been an additional question. Find the absolute acceleration of the carriage. Okay. Now for the second part, we had to find the time the carriage needs to travel a distance of 3 meters relative to the ramp. This means, first of all, we can state the equation for the velocity, relative velocity. In general, it's the initial velocity plus AR times T. According to the problem description, the system starts to move from rest position, meaning that our initial velocity is 0. And now the carriage is traveling a distance of 3 meters. Then we can integrate this equation once more to 1/2 AR T square. And this has to be equal to the length L. And now we can rearrange this equation right here, for the time. And T is equal to the square root of 2L over AR, which is 1.07 seconds. Okay, any questions to the regarding the second part of the problem? So again, this was not necessary. Okay, if not, then let's have a look at one more.
Sorry,
Yes.
sorry, Prof. I didn't really get. I understand the formulas you use here on the equation of motion here. When we have VR is equals to ART, then I don't know. Did it give us the value for XR?
Yes.
Or are we going to calculate that?
No, it's given because it's asked for the distance of 3 meters.
Okay.
If you read the problem, it says how much time is needed to travel a relative distance of L equal to 3 meters on the ramp.
Okay, thank you, ma'am.
So this is given, and then I substituted here. Okay.
Professor, I also have a question.
Yes.
In this question, the word relative was used, so it was easy to understand it. But had the word relative not been used, then would we have used the absolute acceleration, which is a1, or still the relative one?
Well, in this problem, the acceleration relative to the ramp was asked for. So we wouldn't have been able to compute the absolute acceleration. if you're thinking of exam problems, then it will also be indicated, and it will be asked for the absolute acceleration of the carriage, for example. And then you know that you have to compute the absolute acceleration, which would require this step here, right? So you can know from the problem description what you have to do.
All right.
What you have
Thank
to
you.
do.
Thank you.
Yep. Okay. Yes. Question in the chat. It's in integration. Okay. All right. Let's have a look at another exercise at problem 417. Just have to copy it from the exercise book. Okay, there it is. Okay, we have a merry-go-round that rotates in a horizontal plane. And so a similar problem to the very first problems that we discussed. The angular velocity is given with 0.5 per second, and the angular acceleration is given as well. And at a distance of 4 meters, as indicated in the diagram, there are gondolas, like a smaller platform with 4 seats. And on this platform itself has a radius R2 of 1 meter, and they rotate relative to the bigger platform with an angular velocity omega 2 and an angular acceleration alpha 2. And then we have to find the force a seat has to absorb from a person that weighs 75 kilogram for a seat in point A. So this is the seat that's being referred to in the problem description. Okay, now since this is the last exercise I would like to discuss before we move on to chapter 5, I will give you enough time to solve this problem on your own and start solving from the beginning on. So first of all, I'll give you about 10 minutes to draw the free body diagram, meaning you have to decide what kind of system is this, what accelerations have to be considered, which are the directions of the accelerations, and draw this all in your free body diagram. And then we start discussing the free body diagram. If you're done with this fast and you don't need the 10 minutes, then you can start solving the problem, of course. So, but I will not talk about the approach right now. Just decide on your own what approach you have to choose. I will open the sessions and I'll give you 10 minutes time until 12:34. Okay. Okay, so I think it was enough time to draw the diagram. And first thing, you have to decide what type of problem it is and how we can describe the problem. These rotating platform problems are very similar to the ones we did in chapter 1, the person walking on a platform. So this is a typical point mass problem. Our seat A, the position we want to describe, is our point mass that we can describe on two systems. The leading motion is the rotation of the platform, of the big platform itself, with omega 1, alpha 1, and our relative motion is the rotation of the smaller platform with omega 2 and alpha 2. Now, if we have a look at the diagram, here it is. Of course, it's okay if you draw the full system and include your accelerations there, but you can also simplify the system given only considering the relevant information. So we have the center of rotation of the platform and the smaller center of rotation of the small platform, the point A, and our leading motion are the purple vectors with omega 1, alpha 1. It's a rotation. That means we have to consider normal and tangential component of the acceleration. And the relative motion is also a circular motion with omega 2 and alpha 2, and the normal and tangential component of the acceleration accordingly. And then, since our leading motion is a circular motion, we have to consider Coriolis acceleration. So we have to find the correct direction of Coriolis acceleration, which is the one depicted in my graphic here. Okay, are there any questions regarding the diagram?
Yes, ma'am. Concerning the Coriolis acceleration, why should it face in that direction?
Well,
And
yes.
I don't really get this leading motion of a thing.
The Coriolis for the direction of the Coriolis acceleration, you have to apply the right-hand rule. Maybe you just write it down to remember how it works. Your thumb of the right hand corresponds to the axis of rotation of the leading motion. So in our situation, it points upwards, out of your plane of paper. Then the index finger indicates direction of the relative velocity. The relative velocity points in same direction as the tangential component of the relative acceleration, downwards in our case. Then the middle finger indicates the direction of Coriolis acceleration, which shows the direction as in the diagram. And then that's how you find the direction. Axis of rotation corresponds to the thumb, index finger, direction of relative velocity, and middle finger, direction of Coriolis acceleration. Okay, other questions? All right, if not, then the next step is solving the system, of course. We need to find the components of the acceleration and the absolute acceleration. And once we know the absolute acceleration, we can compute the force acting on the seat. So as we learned the procedure in chapter 1, state the accelerations for the leading motion first, then the relative motion, Coriolis acceleration. And once we know the accelerations, we can draw the free body diagram for the forces and solve for the forces acting on the seat. Okay, I will open the breakout sessions again. If you have any questions, call me into your session or ask in the main room as you prefer. Let's start. To the question in the chat, for the forces, you need to consider the weight of the person. Otherwise, you would not be able to compute a force. First step for solving this problem is solving for the accelerations. And then we are only considering the inertial forces acting on the seat, not the force perpendicular to our plane of motion, which would be gravity, of course. So only the inertial forces, which act in normal and tangential direction. Gravity acts on the seat as well, but it's not in the plane of motion, our system here. Okay, yeah, no force of gravity. We do not see the force of gravity in our diagram. Okay.
Excuse me, Professor.
Yes.
Why don't we consider the gravitational force?
Because gravity acts perpendicular to our plane of motion. The diagram given is from top view. So we are looking at the roundabout from above, and
Yes.
gravity acts downwards. But we are only describing the in-plane motion. It's a two-dimensional problem. So
but the seat also has to hold the weight of the person, right?
Yes, of course, but not in the direction that we are discussing. But of course, there's also a force in direction of gravity, acceleration of gravity. But we do not see this force. If we would have another view, a side view of the system, as in the problem we discussed last week, then we could draw the vector for the force of gravity, and of course we can compute it as well. But here it's not necessary.
Okay, so we just consider the absolute acceleration in the horizontal and vertical direction then.
Yes, exactly.
Okay. All right. Thank you.
You're welcome. Okay, at least as far as I received feedback, you are finished with the problem. Now let's have a look at the result. Here you can see the accelerations, the components of the acceleration, leading, relative, and Coriolis acceleration. So compare with your results to make sure that you have the right answers. I'll just wait a few seconds for you to compare, and then we will look at the forces. Okay, then once we know the accelerations, we can build the sum of the accelerations in normal and normal and tangential direction, and then build the forces, the inertial forces in these directions. And for the absolute force that the seat absorbs in the plane of motion, we can build do the vector addition of the two forces, normal and tangential force, to obtain 104 newtons. Of course, I already discussed with a few of you already, there is gravity acting on the seat as well, but gravity acts in the plane of motion. You can see this. Oops, sorry, wrong color. Being depicted by this symbol. Then gravity acts in the plane, perpendicular to the plane of motion, and does not have to be computed in this case, in this example here. Okay, are there any questions? Okay, great. Then I think it worked quite well, and you were able to solve these problems. And I would like to move on to chapter 5, and we will discuss the theory of chapter 5, which is quite short in this chapter, and then we have time to solve problems regarding this topic in the next week. So that's not the right page. Here. Okay, so chapter 5 discusses the characteristic values of mass, the J that you've seen before, that was given in a few problems already. Now we want to talk about how we can compute the characteristic value of mass. So this is quite similar to the class Strength of Materials that you're hearing parallel to this course, where you learned about the characteristic values of areas. And in our case, we are not solving the integral over the area. We are integrating over the mass of our object. And of course, we know our mass element, as you learned in statics, is density times volume, and the volume can be described by the dimensions in x, y, and z direction, multiplied by the density of the system, of course. Then if we have an object that consists of several components, then we can transform the integral into a simple sum of the individual masses. This shouldn't be new to you. You already used this in statics in engineering mechanics 1 when you computed center of gravities of objects, plates usually, and things like that. And you also know this formula already stated using the integral or the sum. Both is possible. Of course, we will usually use the sum and not the integral. We will break our system down to areas or to masses with specific masses that we know and that we can compute directly. Then for the mass moment of inertia, it's quite similar. We can compute the axial mass moment of inertia for rotation about a specific axis. Here it is stated for the x-axis, which is the integral of the square of the radius in x direction integrated over the mass. And again, if we know our system or our subsystems, we can break it down to a sum, and we do not have to solve the integral. And in y and z direction, it's identical. The equations, of course, are also stated in the formulary for all three directions, x, y, and z direction. Then we have to consider the radius of gyration, and this is the measure for the average distance of all mass components from the axis of rotation. So what does it mean? If we have, like a simple example, if we have a cylinder that is rotating about its center of gravity, for example, with a given angular velocity, then what we are doing, what this integral refers to, is that we break down our system, our mass, our object into a high number of very small masses. Like this is a sum of very small masses, all the individual mass of the system. So for example, along this radius here, we would have all these small mass elements like this. And they have different distances from the axis of rotation, from the center of the mass in our example. And the I refers, the radius of gyration, refers to the average distance of all masses. And then the average distance of all masses, square of the average distance, of course, would be here somewhere. So every mass component has a different distance from the axis of rotation, and then we can build, or we can compute, the average distance of all these components, distance to the axis of rotation. That's what it refers to. And where's my mouse here? What else do we need? Of course, if our system, our object, does not rotate about a main axis, then we have to consider the rotation of we have to consider the postural moments, referring to a rotation about an off-centered axis, for example, which is stated here. And again, if our axis of rotation refers to a main axis, these mass moment of inertias, postural moments, are equal to 0. Yes, in my example, the x-axis is the axis of rotation, pointing outward or inward the plane of paper. Exactly. Okay, then for the mass moment of inertia of simple bodies, there are tables in the formulary. So you do not have to memorize them. You simply have to look them up and have to learn to work with these tables, which we will do in the next week. And then there are simple modifications. For example, a parallel displacement with respect to a main axis. There are tables for this as well, or equations for this as well. And then a second option would be, a simple option would be a planar rotation of the axis, which is stated in the formulary on the same page. So what we will do in this chapter is we will practice defining the mass moment of inertia for different systems, for different objects, and we will discuss how the mass moment of inertia changes when our axis of rotation is not a main axis, not an axis passing through the center of gravity, but a different axis due to a parallel displacement or a planar rotation of our object. So let's have a look at the formulary. That's where we stop. So it's on the next page, page 5. Let's increase this a little bit. Okay, there it is. Okay, so here you have the same equations as stated in the script, of course. How to compute the mass of a system. You have practiced this a lot in Engineering Mechanics 1. We will not practice this here, not spend much time on this. What is more interesting for us is the mass moment of inertia. Equations are stated here, as well as the radius of duration. And then here we have our special cases, parallel displacement of the axis of rotation. If our axis of rotation is parallelly shifted, then we have to consider the Steiner share of the problem, which is this part of the equation here. What this is and how it's computed will be discussed in an example, because it will be much easier to understand than if we discuss this in theory. And here in the box, these are the equations in case of a planar rotation of a system. So these are our general equations. And on the next page, we have the table with the specific examples. So these mass moments of inertia stated in the table refer to an axis of rotation being the main axis. Okay. Then, for example, if we have a cylinder, we have the equation for the mass moment of inertia with respect to the x-axis and with respect to y and z axis, which are identical due to the symmetry of the object. Okay. Then also for cuboid, we have the mass moment of inertia given, always referring to the coordinate system given in our problem description, in our example here. Third object is a long and thin rod, x-axis being the axis parallel to the rod or in direction of the rod. Then it's quite simple here. And the last two examples are sphere and a circular cone. So these are our so-called simple geometries where we know the mass moments of inertia, or where we can use the tables to find them. And if we have a more complex object, we have to either integrate, or we can break it down into these simple forms and build the sum of the components over the components. Okay, that's all there is of theory for chapter 5. We will, as I already said, we will practice this defining the mass moment of inertia, because we will need the mass moment of inertia for chapter 6, when we will discuss general motions of a rigid body, so kinetics of rigid bodies. Then the mass moment of inertia is necessary to describe the motion. Of course, it's part of the inertial moment. Okay, are there any questions so far?
Yes, I have a question to page 16 of the script. Yeah, in the very end, it says DF6, DF5, and so. What are these?
These are the pages in the formulary. Dynamic formulary, page 5.
All right.
So
okay.
if you have, well, here it's page 6, for example, DF6. It's the page number. And the previous page would be DF5.
Yeah, all right. Thank you, sir.
Yep. Okay. Other questions? If not, then I would like to stop here, and then we will practice these this chapter, the theory of this chapter, in different examples next week. For a general measurement of inertia using the integration, for a planar rotation and a parallel displacement of the axis. So all the different types we need to consider. Then I would like to stop here. And as I already told you at the beginning of the class, if you have any questions regarding the class theory problems we solved before, specific problems that you have when preparing for the class or repeating what we did so far, then you have time to ask them right now. If you do not want to ask them in the main group, you can also join a breakout session. Rooms 3 to 8 are empty, so just pick one of them and call me into your session. Okay, and if not, if you do not have any questions right now, then that's fine, of course, as well. I will take some time, I will give you time for questions after every class on Monday. So if you do not have questions today, then maybe next week or in the weeks to come. I think the numbers of questions will increase when the closer we get to the exam. Okay. Well, for everybody else, have a good week, and we continue on Friday.
Professor, I wanted to clarify something. You said something on you give information on our last class, which was on Friday, saying there will be an extra class or something. I don't really know that you're going to give at the end of the class today.
Yes, that's what we are doing right now. I said I will not give an extra class. I said that we will have time for questions. Before we had to switch everything to online, we had the on-campus class, the offline class afterwards, after this class. But there I did the same as we did now. So it doesn't make any sense to repeat myself for the next 90 minutes. But if you have any specific questions, then you have time to ask them right now, if you like.
Okay, but my question is just on chapter 3, where I tried solving a question, but I was not really getting it. I don't know if I can bring that up. That's why.
Yeah, of course. Just you can share your screen, or I don't know.
Oh, my screen.
Well, I don't know what your question is. I will not repeat the classes, of course. Okay, I will not repeat the class from 4 weeks or something like that. But if you have a specific question, of course, you try to solve a problem and you were not able to obtain the solution, then you can ask the problem, the questions regarding this problem. But it has to be a specific problem, not like I didn't understand chapter 3. Please repeat the whole chapter.
Okay, because this is just for me on my notes. Is question chapter 3, question 16. I use my phone. I don't really know how to. I don't really know how I'm going to place it. It's just on the book.
Well, just what's your question? It's a question from the exercise book, or?
Yeah, it's the question concerning the exercise book. And when we talk chapter 3, question 16.
Okay.
Okay, hold on. Yeah, concerning two symmetrical arranged brake levers, and I was trying to apply moments and other things, which I got the steps right, but when I tried to check my answers, I was not getting it. I was shut down by 50 newtons. I was getting 300 newtons while they were getting 250. And for me to calculate my braking torque, which is the friction. I don't really know how I'm going to explain it. Why not seeing it? I don't know. I'm just saying.
Well, maybe you can show me your free body diagram or something like that.
Okay. Well, okay. Well, I don't know if I can share the whiteboard or something. Yeah. Are you seeing this, Ma?
Yes, I can see that.
Okay. Don't mind my drawings. Just A and B.
No, just do the free body diagrams directly. You do not have to draw the original system.
Okay. Well, from here. Okay. Sorry, Ma. Oh, this P1, P2. There's a shoe here, which has a friction acting opposite here. Which I don't really know how. I'm just using my phone or something. I don't really know. So,
well, maybe it's it's easier if you prepare your questions first before you ask them. So you could draw the free body diagram on your paper and take a picture with your phone and then share that picture. Might be easier. What you're trying right now is not yet a free body diagram. And as long as the cylinder in the center is connected to the shoe, the brake shoe, there you cannot see any forces there. And then I don't know what P1 and P2 is.
He had it somewhere, just on my other sheet, but I've solved a lot of questions. I can't really.
Well, yeah, maybe you have to
get it. I don't know if
I cannot understand you.
I'm already doing that now. I don't know if you can skip just a few seconds now.
Yeah, well, maybe there's another question while you're drawing.
Okay.
Okay, just prepare your question first, and then when you're finished preparing your questions, then you ask, okay? And while you do that, another student can ask a question.
Okay.
Okay.
Thank you, ma'am.
Yep.
Thank you.
Professor, just 2 quick questions.
Yes.
In the very beginning, can you please remind, there was a connection between the unknowns and kinematic equations. Can you please remind this relation?
How to know how many kinematic conditions you need to derive?
Yes.
Yes, okay. First of all, you have to decide how many kinematic variables are there in your system. How many types of motion, okay? So, for example, a translation and a rotation, or 2 translations and a rotation, or something like that. It's simply draw them in your free body diagram, like we did for the cylinders and masses connected by ropes, and then count them. It's important that you only count either distances or velocities or accelerations. Don't double, otherwise you would double count them, okay? So for example, you count all the distances, all the translations and rotations that are in your system. Then the number of kinematic conditions is 1 less than the number of kinematic variables. So for example, if you have 4 types of motion in your complex system, then you need 3 kinematic conditions.
Yes, and thank you. One more specific question.
Okay.
It involves the problem. I need to find the number of the problem. Just a second. The problem 311.
Yes.
If you go to the solution, do you see the problem and the solution?
Just a second.
I think we can, if you remember the problem, we can just go to the solution.
Yeah. 311.
311.
Okay, yeah, I have the solution.
Yeah, I understand from where we get the first line, and we derive the delta L1 from it.
Okay.
When I was solving it, I solved it with the numerical method, with substitution method. I mean, I just equated it and started to guess. And when they started from 0, and when they equated, I get the right answer. But now in your solution, you somehow derived delta L1. Just to save the time, my method with guessing, with numerical method, it will work every time, because I didn't understand how you derived delta L1 from this first line.
Well, it's a quadratic equation, the first line.
Yeah.
For delta L.
Yeah.
So you can state, you have to rearrange it. 0 is equal to delta L1 square minus delta L1 2 mg over c, and then etc. Like the Mitternachtsformula or PQ formula.
PQ formula.
Do you know that?
No.
That's when you have a quadratic equation. So you have your unknown, like x squared is equal to a times x plus b is equal to 0. Then you have to solve this equation. Then you have there's a specific formula to solve this equation.
Yeah, and its name is PQ formula.
Yes, there are several names actually, but maybe you probably find it if you type PQ formula in Google.
Yes, that's what I'm going to do now. Yes.
Okay.
Yes, thank you very much.
Yeah, you're welcome.
That's all. Yes, thank you.
Okay, all right.
Professor, I'm done already.
Okay.
With the free body diagram. So I will just be sharing my screen. Yeah, this is it. This is actually the question, and this is the free body diagram.
So,
can you see my screen?
That's not, yes, I can, but it's not correct. In A and B, there's a hinged support.
A hinged support?
In A and B, in the points A and B.
Okay.
So where are the forces of the hinged support?
Okay. Well, I
remember from you remember from statics how to draw free body diagrams?
Yes, yes.
Okay, but it's not correct what you did.
Oh.
Because there are several mistakes. If you cut through a hinged support, you see the forces, the support reactions. So you have to draw the support reactions in your free body diagram. If you do not cut through a system, you do not see any forces. Meaning, if you do not cut through the braking shoe, you cannot see force of friction and R and RL or whatever it is. So you do not see these forces.
To the left side and right side.
Yes, and if you do not cut through the rope, you cannot see P left and P right. Because
I don't really get when you say you don't cut through the rope. I don't get that part.
Well, your rope on the bottom of the system is still there in your free body diagram. Then there are no forces. You do not see the forces as long as your system is intact. If you do not remove or cut through these systems or the components. In the original system, you have the original system?
Yeah.
Yes.
The top part is the original system.
Yes, but without the P1 and P2. That's not drawn in the original system.
Yeah, it's not drawn. I was just recreating it. When I saw it, I just drew the equation. I said bringing out the forces that matters at some point.
No, but that's wrong because it's not there. The force is not there as long as the rope is still there in the system.
Okay. I get what you're saying. So more like since the force is acting on the rope, it should be more like a tension acting and downwards.
Yes.
Like a T1 and a T2.
Parallel in direction of the rope.
Okay.
But, you have to draw two free body diagrams. One of the entire system by simply freeing from the hinged supports, A and B. So the only additional forces in your system and the free body diagram will be the hinged, the support reactions in A and B. Everything else stays as in the figure given. And then your second free body diagram would be the free body diagram of one of the braking shoes, like the banded beam on the left, for example. Then you see the hinged, the support reactions. You would see the forces in the contact point to the wheel, and you would see the rope, the tension in the rope.
Okay. Okay. I still don't concerning the hinge support parts, which is the A part, A and B part. I don't know if with this you can just, I don't really get when you're saying it without saying it. I don't know if you can help me out here. Like if you can
just if you free a hinge support, what support reactions do you see?
From my hinge support.
Yes.
Well,
what forces are absorbed by a hinged support?
I think it should be a force acting downwards and side. I don't know.
Yes,
Perpendicular to it.
Two forces perpendicular to each other.
Forces, yeah.
So, and they have to be there in A and B. They are substituting the support as in statics. That's what you did in statics 100 times, I think.
Yeah, yeah. Okay, I get that part. Then I will try to just remove the row part. Since you said there are going to be two diagrams.
Yeah, then you have to erase all the other forces except of the external force in this free body diagram. And you have to draw a second free body diagram only of the left part of the system or the right part, doesn't matter.
Left side or the right part
of this banded beam, one of the shoes.
Okay, one of the. So you are trying to tell me I should take it separately?
Yes, you need two free body diagrams, one of the entire system, and then the second free body diagram only of one part of the system.
That will be from the base of the shoes.
For example, the banded beam from support A to the rope.
Okay, support A to the rope. Okay. But if I should separate it like that, won't it affect the B part? Because if you see both A and B comes together, there's a rope attached to A and B together to form where the force F holds it. I don't really know.
I didn't understand your question.
Okay, I don't know. With this diagram, can you just like, I don't really get it when you, can you just
I think your problem is statics and not you're not at the point of solving the problem yet. You have to, as in statics, there's an arbitrary system, whatever it is, doesn't matter, and you free the system from the surrounding. So you draw your line around the system, cutting through the hinge support in A and in B. And then you have to draw this system and you substitute the support by the support reactions. 2 support reactions for each hinged support.
Okay.
No other forces at all. Just draw the diagram, the figure given in the problem 316 and substitute the support by the support reactions.
Okay, ma'am.
Are there any other questions?
Yes, Professor, I have some questions. So, can I share my screen?
Yes, of course.
Okay. Okay. Yeah. So do you see it or no? Not yet.
I can't see anything. No, I
No.
think yes. No. I can.
Yes. Okay. So these are very general questions. First of all, this thing. Can we
Yeah.
use
No. A comma instead of a point in decimal symbols. You mean for the no, because it's in English. It's a point.
so we do have to like okay. All right.
Yes.
Then and then secondly, this is if for example this is a system, how
Yes.
would the equations look like as A, like as I've written in A, or like B?
No, the first version, A, is
The
correct.
first version.
So
Alright.
so you add the vectors, and inside of the vectors there can be a positive or negative sign. Because if your vector consists of two, you have a very simple example, but if your vector consists of two components, then there might be one positive and another negative.
Yeah.
So then it wouldn't work with the minus being outside of the vector.
All right. Yeah. That makes sense. I can put that. Okay. And now there are specific ones. For example, just a second. Yeah. On the page 7 of script, it says 1 point. Yeah, 1 point is considered on two different bodies. So I don't understand how 1 point can be on two bodies.
No, for example, it's the chapter 1 problems, point mass. For example, the person on a roundabout that is walking along, I don't know, rectilinearly, for example. Then we first describe this point, the person being the point, on our leading system, the roundabout itself, assuming that the person is not walking. That's what we use as our first approach, our leading motion. We freeze the relative motion, then our point is on the leading system and it's standing there, the person is standing there, and it's rotating with the platform. And then we step on the platform, or we freeze the motion of the platform, and then we assume or we see the person walking rectilinearly, and then this is our second system, the rectilinear motion of the person.
Okay.
So that's the same person, but now the person, the point, moves rectilinearly.
So instead, if we say that it's considered, like if we that this says it's considered on two different bodies. So instead of, if we say instead of bodies, we say it is considered in two different motions, type of motion. For example, example here in this example where the pedal is first considered, the rectilinear motion of the pedal is considered, like the whole motion of this bicycle first of all, and then the rotational motion of the pedal is considered.
Exactly.
So that's what was meant here.
Yes.
Yeah. Okay. Not because the same point can't be on two bodies.
No.
Course, right?
Yeah, but for example, the example we just did in class right now, then the first body would be the big roundabout, the big platform. So our point moves on this platform, and in the second situation, our relative motion, the point is on the smaller platform rotating with omega 2.
Oh yeah. Okay.
Okay, but yeah, of course, if it's easier for you to understand, then it's say different two types of motion or whatever.
All right. And now some colleague of me already asked this question, but you said something which I missed. I was writing something. You said that either consider V or A, not both things, right?
No. Yeah, when counting the number of variables, you can either count accelerations or velocities or distances. Since the velocity v1 is the time derivative of the distance and the integral of the acceleration. So it's one type of motion.
Yeah.
A1, B1, and X1, and that's why I said only count one type of motion: acceleration, velocity, or distance.
So then if we say, for example, number of kinematic variables is equals to number of motions.
-1.
Yeah. Oh yeah.
-1.
No, variables. If we say kinematic variables, then
but it has to be one less than the number of variables. If you have 5 variables, you need 4 kinematic conditions.
No, I mean this here. The number of variables is equal to the number of motions, right?
Motions, yes, type of motions.
Okay. And now this thing, I asked you this, but then I still didn't get it properly. For example, in our question 2.5, and then we discussed many options.
Yeah.
But in either 1 or 2, when we say K moves translational as Z, and then it also rotates about Z. And first of all, I could somehow understand it that you gave us this example of the letter.
Yeah.
And
exactly.
First, like, although when we see a letter coming from this position to this one, we don't see really a rotation and not a pure translation either. But we are saying this because we can't otherwise tell this something somehow in mathematical.
Yeah, we cannot describe the general motion mathematically.
Okay,
and that's
the
why
transition from A to A dash and then B to B dash. Like we can't read. Oh, okay, so then we
we have to break it down to our simple forms of motion.
So that's why we also say, okay, then, okay, if I somehow do understand that K rotates about Z somehow.
Yes.
But then how do we know that it's rotating clockwise? It could have also been rotating.
No, just if you use your hand and hold it, like your straight hand, and you hold it to the line, parallel to the line KZ.
KZ, yeah. Parallel to it?
Like, yeah, just place it above your screen maybe, okay?
Yeah.
And now you know the direction of Z. It moves upwards and to the right. Now do this with your fingers. And K has to stay on downward on this dotted line. Then you can, and if you exaggerate this motion with your hand, maybe I can show it on
or
camera.
you can
look,
maybe here.
Like this.
Yes.
This is the starting position. And now your fingers move up and K has to stay on the line. So it goes like this. You see that?
Yes.
And then you see the direction of the rotation?
Yeah. So that's if it goes that way, but then we consider it sort of this way. All right. Yeah. And this is fixed. Since it also says that it has to be calculated in the depicted position. All right. Yeah. So then that was it. Thank you very much.
Yeah, you're welcome.
Rehan, can you just for a minute show back the same screen and the same diagram? Because I just have a very tiny question from the same last question that we were discussing.
Yeah. So 2.5, right?
Yeah, the same one we were talking about. All right, perfect. Can you please zoom into the main diagram which is given with the question?
Not the main one.
Okay,
the one given. All right, here.
Right, perfect. So, Professor, my question is, when we say K rotates about Z, for me, it was a bit difficult to imagine, but so this is how I understood it. So when we're talking about K rotating about Z, basically what we're talking about is that Z over here is going to remain fixed, and this K is going like this in a circular motion. Is that, am I imagining it correctly, or is it wrong?
Yes, that's correct. For the rotational part, we assume that Z is fixed and K rotates about Z.
All right, and we have to do this with every question when we are talking.
If it's a rigid body, yes.
Okay, not Not with the relative motion and...
No, first thing we have to do is distinguish between point mass and rigid body. If it's a point mass, we use the approach leading plus relative motion. Both can be either translational or rotational. And if it's a rigid body, then it's always translation plus rotation. These are the only two approaches we have.
All right, understood. Thank you.
Yep, you're welcome. Okay, other questions? Okay, well, if not, then I think we can stop here for today. And there will be time for questions again on Monday next week. Of course, throughout the class as well, but additional extra time for questions on Monday after class next week. Then have a good week and see you on Friday. Bye.